All right, I think we can go ahead and get started. There's been a little bit of change in schedule. This is going to be a 2.5-hour monad tutorial now. So if you all are ready, we'll get started. No, I'm going to be talking about the dream of the 90s today. Sadly, not talking about this dream, but this dream. This is the dream of pure, lazy, functional programming. For some of you, it might be more of a nightmare than a dream. But yeah, so this is a group of functional programmers in the 90s working on what would become Haskell. This was happening in like 1991-ish. And it turns out they were in good company. All of these technologies came out of the 90s. How many of you use one of these? Yeah, what about 2 or more of these? Yeah, I mean, this is like basically everything we still use right now. This is Linux and FreeBSD, the operating systems, Java, JavaScript, Python, Ruby, the languages we use, the databases that we still use, Postgres and MySQL, despite the kind of NoSQL buzz, we still use these databases. So there's a lot of really good ideas that came out of the 90s. These kind of were popular in the 90s, Haskell not so much. But I think Haskell made some really interesting decisions 20, 25 years ago that are really kind of starting to pay off now with the challenges and the computer architecture that we have today. So I'm going to talk about that, kind of give a motivating example for why you'd want to use a language like Haskell, and then give a little bit of an experience report of using Haskell in production for a couple of years so you can see that it is actually possible to do that. So if you're not familiar with Haskell and you start doing some reading on the internet, you'll likely come across a definition kind of like this. And around 2010, when I started learning Haskell, I was reading the Wikipedia page about it. A friend of mine was doing some Haskell programming, and I read this, and it made absolutely no sense to me whatsoever. Like, how can such a short sentence make no sense? And it kind of like frustrated me into learning Haskell, because I was like, I'm really upset that I don't understand this sentence. So I learned Haskell because of that. And so if we kind of start picking this sentence apart, we can kind of break it into some parts that make more sense. So Haskell is a standardized, general purpose, purely functional programming language with non-strict semantics and strong static typing. Okay, there's a lot to kind of unpack in here. So let's do that. So Haskell is standardized. Unlike a lot of languages that you've used, there's actually a specification that is divorced from the implementation of Haskell. So there's been a few versions of this specification, Haskell 1.3, 1.4, Haskell 98, Haskell 2010. They're working on Haskell 2020 right now. And this is separate from the compiler that most of us use, which is called G8C. There's other implementations of Haskell that follow the specification. And what's nice about this is since the specification is written before the actual compiler is released, it means that bugs in the compiler don't just become accidental specification, which seems to be the case in a lot of other languages. Haskell is intended to be a general purpose programming language. So we can write desktop applications, web services. We can do embedded development, data science, research. This is in contrast with something like a single purpose language like PostScript for printing, CSS for style sheets and web pages, or JavaScript, which has no purpose. It's a purely functional programming language. This is where things start to get a little confusing or intimidating even. So let's kind of talk through with a pseudo language what this means to be purely functional. We're going to talk about a property called Referential Transparency. It turns out to be pretty simple. So this is our kind of made up language right here. And we're going to say x is equal to 5 plus 2, that's 7, and y is equal to x plus 3, so that's going to be 10. If a function or an expression is pure or referentially transparent, we can replace, so we're going to comment out this x assignment here, and we're just going to replace where we used to have x with 7 there. And if a language has this property, we can do that all we want, and the result of running the program is the same. We get the same expression. So in this example, this is definitely true. Before we even run the program, at compile time, we could do this and it would be totally fine. But in our made-up language, let's say that if we use semicolon, we can kind of do multiple things in an expression. So we're going to say X is printing the hand-wavy emoji, and then we're going to return 7. And then Y, same expression, X plus 3. And if we were to comment this out and replace X with 7 here, we've kind of lost the fact that we are printing out this hand-wavy emoji. And so in a language like this, we either don't have referential transparency, this is not a purely functional programming language, or we need to somehow represent in the return type. So instead of returning 7, we need to say like, here's 7, but also here's some data structure that represents that we're gonna print some data out as well. And so Haskell has this property. You absolutely can do things like print things out. But instead of just returning 7, you're also going to say, here's 7, but also here's some set of instructions for how to do the effects that I intend to do. Next, we have non-strict semantics. This is kind of a less specific way of saying that we have lazy evaluation. You've probably seen something like this in other programming languages where you can have really big lists that are processed lazily. So in Haskell, we can create a list from 1 to 9 million or whatever that is. And at this point in the program, when we've just defined this expression, Haskell hasn't done anything to actually put this into RAM. It just says, I know how to do this, and when you're ready for it, I'm going to start doing it. But further, it can actually only compute what you need of this. And so if we call this function called take, which is just going to take a subset of the list, and we print this out in the REPL, so Haskell has a read eval print loop, then we can print out the first 3 numbers in this list, and we never actually have this full list in memory. We can do some more complicated things, like we can actually sum this list together, but not actually produce the list and then accumulate through it. So we can actually sum this list without ever having 9 million elements in memory, which is pretty cool. We have strong static typing. Okay, so if we kind of break this into 2 halves, we have strong typing and static typing. And each of these can be contrasted with its opposite. So we have strong versus weak and static versus dynamic. And these are 2 different independent variables that can vary separately. So let's give an example of a language that has sort of the opposite end of the spectrum, which is weak dynamic typing. So most of you probably recognize that this is JavaScript. And if we add the number 5 to the string 3, JavaScript decides that that is the string 5.3. Maybe it could have been the number 8, but this was that lack of a specification that they decided to do. So this is a weak dynamically typed language. Weak in this case means that we're able to just sort of coerce values together without calling a function like integer to string or string to integer. It's dynamically typed, which means that all type comparisons are done at runtime. In this case, it's happy to just combine these together, and there's no problem. If we take a look at a language like Python, we try and add a number and a string together. At runtime, so dynamically typed, we have strong typing. So it's going to say, at runtime, we throw an exception, and we say, we can't add an integer and a string together. So this makes a little more sense. Haskell, we have strong typing and static typing, which means that we can't just coerce our integer and our string together, but before we even run the program, Haskell's like, whoa, that doesn't make any sense. This program is going to fail to compile. You'll fix the issue, then you can run the problem. So you'll never have an exception like this at runtime in a Haskell program, because all of that is sort of solved for you before you run the program. So we've taken a look at kind of the sort of dictionary definition of what Haskell is. I'd like to talk about a few of my favorite sort of Haskell features and one of the reasons that we're using Haskell in production. Some of the things that were kind of decisions that Haskell made a while ago that I think are really starting to pay off now. And so we'll see that through concurrency, parallelism, and type safety. So first, Haskell is a concurrent language. We have lightweight threads, very similar to a language like Erlang or Go, and we're able to create millions of these threads and only have a handful of operating system threads that are actually running under the hood. So let's make a quick example of a TCP server, for example. So we're going to create a socket. We're going to use the listen system call, and then we're going to use this function called forever, which is basically the same as like while true. We're going to call accept to get a new connection. So somebody has tried to connect to our server, and then we're going to use this function called fork.io, which is like the Go statement in the Go programming language. So basically what this is doing is this is creating a new thread that's going to run this handle function with the new connection. And then this thread that we're in now is going to continue looping while this runs in a separate thread. And what's nice about this is we don't have to do any callbacks. We don't kind of have callback spaghetti hell code. This thread that's running handle, all it has to do is sort of concern itself with the single connection that it has. And this main loop only has to worry about accepting new connections. And even though this sort of appears to be blocking I/O, which has some positive and negative trade-offs, under the hood, this is actually working very similar to how a language like Node.js would use epoll. So Haskell is basically just at runtime doing the right thing using epoll or KQ or whatever your operating system uses for evented I/O. Next, we'll talk about something called software transactional memory. Normally, when you have multiple threads and you try and access a shared variable, that's a really big source of race conditions bugs, just sort of synchronizing on a single variable. Synchronizing on multiple variables is like, you've kind of got to be an expert in concurrency, and then you got to really test it. In Haskell, we have a really great way of doing this in a simple and correct way called software transactional memory. And it works very similar to transactions in a database. So inside of this atomically call, which does exactly what it says it's going to do, we're able to read and write to any number of shared variables that we want, and other threads are going to see the state either before this entire thing runs or after this entire thing runs. If anything fails in this atomically block, the entire thing is going to roll back. It'll never be seen by anyone else. So this is a really nice way for us to do multiple things on shared variables in a way that we don't have to worry about taking locks in the correct order, doing lock spinning. So in this case, let's say we have like a chat server, kind of a pub sub thing. We're going to increment some integer, which is just how many users are sort of currently logged onto the system, and then add this user that just logged on to some subscriber list. And so both of these are either going to both happen or neither happen. And other threads will never see this in-between state. Well, they'll never see this happen and then an exception runs. Next, we'll talk about parallelism. So we talked about concurrency just a minute ago, and in Haskell, we tend to make a distinction between concurrency and parallelism. So you can have a concurrent system even with one core. So back in the 90s when we had one CPU, one core systems, we still had concurrency. We could have multiple threads that on a computer with a 1 gigahertz processor, it's just multiplexing those threads quickly back and forth. So we get kind of the illusion that they're running at the same time. With parallelism, we're looking for something different. We're looking to actually exploit multiple cores to do things physically at the same time, not just the illusion of at the same time, but we're looking to speed up some process, not so that our programming kind of becomes easier or the user sort of is able to check their email and listen to Spotify at the same time, but we're exploiting multiple cores to do things at the same time. And what's nice about parallelism in Haskell is, unlike concurrency, this is completely deterministic. So with concurrency, when you have multiple threads running, it's sort of up to the thread scheduler and your use of synchronization primitives to decide the order that the threads run. And so depending on the order of execution, you can get a race condition that happens some of the time, but not other times, or works on my laptop, but not yours. With parallelism in Haskell, it's actually completely pure, which means that every single time we run it, it's the same as if we just ran it without parallelism. And unsurprisingly, it's pretty simple to do. Some of you are probably familiar with the function called map, which applies a function to elements in a list. We have a function called parmap, which is basically parallel map. And so we can create some list of tasks. Let's say this is, probably in reality a list of 100 or 1,000 elements. And we're going to run this process function. Maybe it takes 50 milliseconds or a second to run. And normally, if we were to just call this map function on it, it's going to sort of process these in serial. But with parmap, we're able to take advantage of all of our cores to work on these at the same time, but know that we're going to get the exact same result as if we just used the regular map function in Haskell. And actually, the type of this, if we were sort of looking at the types in Haskell, would be the exact same as if we did it just in serial. Next, we'll talk about type safety. So Haskell gets kind of a bad rap for having a really complex type system. But you can actually take advantage of just the sort of really simple features of the Haskell type system and go a long way. So I'm going to give a 4-line example that I think is a pretty interesting example of using just really basic features of the type system to get some interesting properties. So let's say we have a web application and we're storing users' passwords. We're professionals, and so we're going to store the hashed password in the database. No plain text passwords. And we want to sort of make sure that that's what we're doing. We don't want to have some part of the code base where we accept the password and we accidentally don't hash the password. We also don't want to hash the password twice or more times, because hashing a password once is not the same as hashing it twice. And so we can create some types in the Haskell language to help us out, and then use those types in our functions to make sure that we hash a password exactly once before it goes into the database. So we're going to use this new type keyword. We're going to create a type called plain text password, and all it is just a wrapper around string. So we get to take advantage of all of the functions, operations, representation that already come from a string. We're just saying that plain text password is kind of like a specific string. It can't be used in places where you would want a string, but the internal representation is the same. So hashed password is going to be the same thing. It's just going to be a little wrapper around a string. And so this hash password function is going to take a plain text password, and it's going to return a hashed password. And by only exporting this function and plain text password, it means that consumers of this module, the only way that they can even construct a hashed password is by calling this hash password function. And you notice that if you have a hash password, you can't hash it again because it's the wrong type. And so our store password function, which is going to store the password in the database, it takes a hashed password. And so we've now prevented a whole class of bugs where we don't hash a password or we hash it more than one time. And it turns out that most sort of production Haskell programs have types like this for pretty much every value in the domain. So instead of using a string for an email address, we create a type called email address. Instead of using integer or UUID for an ID in a database, we create a user ID type and an organization ID type and a user preference ID type. And they're literally just one line to create. So it's not like we're creating a new module that has some big Java object for this. It's really simple to do this. So there's not much friction in doing it. It also provides really great documentation. If I have a function that is from string to string, that doesn't tell me a ton. But if I have a function from email address to domain, even without looking at the name of the function, you can probably have a pretty good idea that it's going to extract the domain name from the email address. So it's going to return gmail.com. And so that's kind of a brief overview of why you might want to use Haskell. Haskell, as you're probably aware, is not a particularly common language to use in production. Some would even say production Haskell is an oxymoron. I'd like to tell you that it's not. Things have changed a lot in the past few years. How many of you have played with Haskell more than like 2 years ago? Okay, 1 or 2 people. So things have changed a lot. Tooling has gotten a lot better in the past like 18 months or so. So I'm going to talk about using Haskell in production at the company that I work for called Helium. We've been using it in production for a little over 2 years. So Helium is an Internet of Things company. We make both hardware and software for commercial and industrial applications for people who are building IoT products. And most of our backend services, of which we have a few, are written in Haskell. So this is kind of an experience report now of using Haskell for a few years in production, watching the code base grow, overcoming some challenges, seeing some really nice things about it. So just kind of starting with some anecdotes, this has been the lowest defect rate code base that I've ever worked on, which unsurprisingly is pretty nice. It's been the easiest to refactor. We've actually found that the more code that we amass, the faster we're able to develop. Typically speaking, the bigger a code base gets, the harder it is to change anything, because you change something here and somehow this thing is affected, or you change something here and you've got to figure out everything that kind of depends on it. And it's actually been fun to do those refactors. It means that we're not afraid to kind of iterate and improve parts of the code base as we go. There's no kind of scary things to touch. And we found that for the most part, the community is big enough that we're able to find open source libraries for pretty much everything we need. You know, I'd be lying if I said that there's as many libraries as they are in like the Ruby or JavaScript community, but it's big enough that you're not going to have to write sort of everything yourself, doing typical kind of back-end web application type development, data science stuff. You're going to find libraries for pretty much everything you need to do. So this is kind of seen through the lens of our experience, which is with about a 45,000 line code base. We have 5 or so developers at any time that are working on the Haskell code base. We have people kind of rotate in and out sometimes. And we have about 6 services that are in production that are built in Haskell. And so we'll talk now about building Haskell code. What does it look like to use the build system? How fast are compile times? Deploying the code, how does it compare to deploying with something like Ruby or Python? Monitoring the code in production. Once we've written the code, that's sort of just the beginning. We have to actually sort of make sure that it works now in production. Testing the code. Haskell has some really nice libraries for testing that I'm excited to talk about. And then developing code. We'll do a little kind of live refactor of something to kind of see how we use the type system to sort of change our code. So first, we'll talk about building. There used to be a build tool in Haskell called Cabal. There still is. And there was kind of a sort of affectionate name called Cabal Hell, which is basically just this build tool was written a while ago, and it was sort of fit for purpose 10, 15 years ago, and hadn't really kept up with how software development was changing. And so a lot of people had pretty poor experiences when they first started using Haskell. The build system that you use is like a pretty important first impression for a language, or even 1,000th impression. But I'm happy to say that as about a year and a half ago or so, Cabal Hell is pretty much gone. So there's a new build tool called Stack, which came out about a year and a half ago, that is dramatically simpler. It's not perfect, but it's certainly better than the typical build tool that you use with Ruby or Python. So it kind of leaped us forward quite a few years. So here's a little example of, it's a little blurry, taking a project that used to use Cabal initializing it with this build tool called stack, and then building it. So we see something that used to be kind of a pain is now something that we just call a single function, or a single command rather, to initialize it, and then we can build our project. And the way that it's able to be so fast is that our dependencies are typically immutable. So if we depend on some JSON library at a particular version, it turns out that all the projects on our computer can share and link against that dependency. So typically kind of having global dependencies is sort of a big no-no. But that's because it sort of can force us to use the same version of things throughout our system. But if we allow our global dependencies to have multiple versions of the same library, then we can share them in our project. So creating a new project that has 25 dependencies, if they're the same version that I've already used on another project, I can reuse all of those, and then the compiler only has to build my code and just link against those existing dependencies. And so we have packages that come with the compiler itself. Those are all immutable. They're tied to a specific version of the compiler. We have packages for a particular snapshot. So Stack has this notion of a snapshot of packages. So instead of just depending on a bunch of libraries at individual versions, we actually have kind of an entire ecosystem of packages that are versioned with a single number. And so you can increment that version number and upgrade all of your packages. If you have a specific version of a dependency that you want, you can override that. And so that becomes a project-specific dependency. And so upgrading all of our dependencies becomes as simple as changing the sort of global dependency number and then rebuilding our project. So we're able to keep up with security patches, APIs changing really easily, and then only where we really care about a specific version of a library do we kind of override that in our file. But for the most part, we find that every couple months we just upgrade that version number, build the project. If there's any compiler failures, we go fix that to update to the new API, and then we're done. Typically speaking, compiled languages kind of get a bad rap for the sort of interactive development cycle. And it's true that if you're building your Haskell code from scratch with all optimizations on, it's not going to take a few seconds. But it turns out that there's some tricks that we can use. Haskell does have a REPL, which means that it can actually interpret code for development. And so even for a relatively big project, we're able to get really fast feedback cycle on whether our code compiles or not, but even run it as well. So here's a little example of making a change to a web server. So we're going to change some text, and we're using a tool. It's a little blurry, so you can't see. But basically what we're doing is changing the text in the source code, clicking save. This tool is automatically recognizing that the file has changed. It's recompiling the project, and then it's restarting the web server, and then all we have to do is refresh the web page. So if you're coming from a language like Ruby or Python or Node where you're used to this kind of interactive workflow, it's actually possible to replicate it completely in a language like Haskell, even though it's kind of known for having a more traditional sort of C or Java-like compile experience. So this is an open source library that I created called Ordeal that we just saw there. When we build our Haskell code, the result of it is a statically compiled binary, just like you would get with C or Go. And so it means that deploying the code is really simple. So when we deploy our code, we're creating a tarball. So let's say we're writing a web application in Haskell. We have our images, our JavaScript assets, our style sheets all in a directory. We put our Haskell web server or our web app inside the bin directory. We tar this up. We append the Git version to it. And then on the actual production web servers, all we have to do is untar this. We don't need any of the Haskell compiler, toolchain. Everything is already compiled for this system. And to update the code, we're just going to update a symlink from this current directory, which represents the version of the application we're running in production. So we're just changing the symlink to reference the new version of the app. We're not replacing the old version. We're not doing a git pull and kind of clobbering the code. So we can actually have multiple versions of the app on our file system at the same time. And then we just restart the application. If things go wrong, doing a rollback is just as simple. All we do is update the symlink to the old version, which is still on the file system. So now we don't even have to pay the penalty of downloading a few megabytes from S3, and then we restart the application. For our stateless services, so most of our web applications are just stateless business logic Haskell services. They use about a whopping 60 megabytes of RAM in production. So we're able to pack these on relatively small, affordable machines. And because of some of the concurrency and parallelism features that I was mentioning earlier, our applications just running a single process are able to take advantage of all the cores on our machine. So we don't have to run multiple Node.js processes to sort of scale our Haskell process to multiple cores. It sort of just happens automatically for us. We just set a flag telling Haskell, I have 8 cores, I have 4 cores, and it does its thing. Next, we'll talk about monitoring our application in production. So we've written the application, and now we're running it. Our job as engineers is not over. We have to sort of make sure that this application continues to run smoothly. And typically speaking, you're going to use a lot of the same tools that you would use in any other language to produce metrics to someplace like Circonus or Librato. There's also an open source tool called EKG, which is going to give us insight into the Haskell runtime. So we can see how much memory are we using at any given time. What's our allocation rate? How long are our GC pauses? And so we can look at these either on a little website that has live statistics, or we can ship this off to our monitoring sort of aggregation service. Logging is very similar. Just like any other language, you can log to standard out, log to a file, log to syslog. In our case, we have all of our services logged to syslog. And logging is pretty much the same as it'd be in any other language. So in this case, we're going to log an info line and then log a warning line. We have that set to go to syslog on the local machine, and then that forwards it to our syslog destination. In our case, we're using a service called Papertrail. And so as far as Papertrail is concerned, it doesn't care what language this is coming from. It's not any more difficult if it's coming from Haskell. It's just receiving a syslog message and aggregating that, just like it would for a Ruby app running on Heroku. Next, we'll talk about testing our application. So despite kind of the reputation that Haskell has, or what some people will tell you, you still need tests in a statically compiled language, even one that has a great type system like Haskell. But we are equipped with a really phenomenal testing library called QuickCheck. So QuickCheck kind of takes a different approach to testing than you may be used to. So typically when we write tests, we have some input, and then we sort of know ahead of time what we expect the output to be. So we say, okay, test that 1 plus 3 equals 4, and we write 10 of those cases. Actually, we probably write 1 of those cases. But so QuickCheck works a bit differently. It says, tell me some property about your function or your system, and then I'm going to randomly generate inputs. And for each of those randomly generated inputs, I'm going to test and see if that property still holds true. So this is actually an example of a real test that I wrote. And so basically what we're doing is testing that when I create an event, which is just some domain object in my domain, if I encode it into JSON and then I decode it into JSON, decode it from JSON, it should be the same as what I had in memory before. We're basically testing, okay, I have some value maybe that I read from the database. I'm going to encode it in JSON, send it to someone else over a socket. They're going to read it back. It should be the same thing, that I had over here. That seems like a pretty simple and important property. And unsurprisingly, when I ran it, it failed the very first time. And so this is the random event domain object that it generated. And it turned out that this timestamp was kind of the field that was messing things up. More specifically, I started kind of playing around in the REPL, and so I printed out the timestamp. So we see this is kind of the partial seconds here. But when I encoded it in JSON, I only had 3 decimal points of precision rather than 4. And so in practice, that's probably not that big of a deal. But just in this one-line test, I've now learned this like pretty interesting edge case about my JSON encoding library. This is not code that I wrote. It's just built-in timestamp JSON conversion from some library that I had. And so with quick check, we're able to find all sorts of interesting bugs and business logic issues in our code, but we're also able to learn kind of about the edges of our dependencies as well, all with these really typically relatively simple properties. And once I fix this, I can now run this test overnight and literally test hundreds of millions of these random examples. So instead of spending the time coming up with some kind of lazy canned unit test examples, I get to spend a little more time coming up with an interesting property and then let the computer do the work of coming up with the actual examples, running it for as long as I'd like. So next I'd like to do kind of a little live refactor demo. Check on time real quick. Showing how we can use the type system to change some code. Let's see. How is that font size for everybody? Bigger? How about now? We're good? Okay, so let me kind of explain what we have going on here. So in this top window, we have the code that we're going to be editing. And then this bottom terminal, I'm going to run a command that's just going to watch our code changing and recompile it. So we'll see how quickly we do this. So we're using a tool called GHCID. And all this is doing is just watching our files and recompiling. Okay, so we're starting off with a module that compiles cleanly. And I'll kind of explain what this code is going to do. So this is kind of a simple representation of something very similar to what we do at work. So we have some users in our system. We're working in IoT, Internet of Things. So we have a sensor. A sensor belongs to a particular user. We have a kind of fake database call that can list all of the sensors for a particular user. Let's say this is a web application, and so we can read a cookie from the user in their request and get the user that's associated with the request. And then we just kind of have a declaration of an example user. In our main function, we'll grab the currently logged in user, we'll print it out, we'll list the sensors that they own. So we'll sort of ask our fake database, hey, give me the list of sensors for this user, and then we'll print that out. And so let's say that our application is going successfully and product management comes to us and says, our users really want organizations so that they can join an organization with the rest of the folks in their company. And so we kind of want to change the ownership. So now a sensor is part of an entire organization. It's not owned by an individual user, but everyone in the organization should be able to see it. Imagine in kind of a real world example, this is not a 30-line example, but this is like your entire product. You now have to sort of change the graph relationship between your domain objects to be owned by an organization instead. That's the kind of thing that in a lot of other languages I'd be really afraid to do, because I'm going to accidentally thread a user where I should be threading an organization, or vice versa. So let's kind of lean on the type system, just using really simple types to allow us to make this refactor. And we'll see that the first time we run the program, it's going to do exactly what we expect. So quick overview, we have a username. So just like I was mentioning before, we're kind of using these domain-specific types to help us out. We have an email address type. We have a user, which has a name and an email. We have a sensor, which has a ID. And then the sensor is owned by a user, so it kind of references up to the user that owns it. If we give this list sensors for user function a user, it'll return the sensors that they own. And so let's start by copying this and creating an org name function, or an org name type rather. Okay, so that compiles successfully. Let's create an organization, and we'll give it a org name. It doesn't need an email address. Okay, so that compiles fine. Now let's say that a sensor should be owned by an organization. Okay, so now that's failing to compile. Let's see what. Okay, so when we create our fake sensor from the database, we were passing a user to it before. Now we need to pass an organization. So let's create an example org. And we'll give it the name Philly ETE. Okay, and so where before we passed example user, we now need to pass example org. Okay, so that type checks. Let's update our query to take an organization. So in some separate code, we've made like a database migration change so that in the database, sensors are owned by organizations instead of users. So this will take an org now, and let's change the name of the function. So list sensors for org. Okay, let's compile that. Okay, not in scope. All right, so we changed the name of that function. Now it's list sensors for org. Okay, so now we're trying to pass a user into this list sensors for org function. And so when we ask for the sensors for the organization, we need to somehow have an organization here. Let's see. We can, in the user value, add the organization that they belong to. So let's add that. Let's compile it. Okay. And so when we create our example user, we need to specify the org that they belong to. Okay, so we're still passing in the user for the list of sensors. And so now we'll just call this function that retrieves the organization from the user value and recompile it. Okay, so that compiled successfully. Let's compile it on the command line and run our program. And so we can see now when we ran it, we're still able to get the user printed out and now print out the user's list of sensors by sort of going through the organization that they belong to. And so this is obviously kind of a simple canned example, but it actually scales really nicely to projects that have tens or hundreds of files and thousands of lines of code. We sort of make the beginning changes that we want, and then we just follow the type compilation errors as they happen, and we're able to see that really quickly as we go. This is obviously a small file, but the compiler is smart, and it only recompiles the code that we change or code that depends on code that we change. So even in a big project, we get feedback really quickly, even faster than you would get in kind of a test-driven development sense. We're able to get feedback really quickly. All right, so let's switch back to this. Okay, so I'd be lying if I said that Haskell wasn't without some challenges. Otherwise, we'd probably all be using it. One of the first one that we ran into is lack of escape hatches. So in a typical programming language, we sort of strive to do the right thing, and then if it gets hard, we sort of just give up and do an ugly thing. And that's just kind of socially acceptable in most programming languages. Haskell really doesn't want you to do that. And so we had a few kind of close calls where we were really trying to do things the right way, but we're not working in academia. We actually have like deadlines and have a business to run. And so we're starting to look, okay, what sort of like just hack can we implement? And it wasn't always obvious what the hack was. In the end, we were always able to kind of figure out a way around it, but the escape hatches are not as obvious as they would be in kind of a typical language where even in a function that adds two numbers together, you can like read a file or something. There's always some kind of escape hatch that you can use, and you kind of feel dirty and regret it, but it works, and you ship your project, and you still get paid. So that was something that took us a while to kind of figure out the lay of the land for, okay, if we're not able to figure out the elegant solution for this, what can we do to kind of still deliver the product? Our customers don't care that we use Haskell, right? So we still, at the end of the day, have to actually ship a working product. Debugging Haskell code is different than other languages. If you're coming from a language like Java or C, where you have pretty good like step-through debuggers, debugging Haskell code is going to be different. You'll typically find that you have a lot less kind of simple logic bugs, but when they do happen, there's no kind of mature, traditional step-through debugger. So you kind of resort to println debugging, which even when I use other languages, I'll admit that I do. I think probably a lot of us still use println debugging, especially in languages like Ruby and Python. But this is something just to kind of be aware of. Debugging is going to be different, and there certainly are some tools that you can use, but they may not be familiar if you kind of are expecting like a GDB-like experience. So yeah, Haskell has been with some challenges. I think it's really paid off for us. Like I mentioned before, it's been the only project I've worked on where, as we've added more code, our team has moved faster rather than kind of slowing down as we've amassed like all this technical debt. So that's been a really rewarding experience. Anyway, that's the end of my talk. I believe I probably have a few minutes for questions. Yeah, Jessica. I think there's a mic that we'll bring around.
Those log statements, the log error, log warning, are those like an escape hatch, or do you have to run them in the IO monad?
That's a good question. So yeah, I did elide over some types there. So typically, the short answer is that they do run in the IO monad. There's a module called debug.trace, which does allow you to just log things to standard out or standard error and pretend that you're not doing it. And it's really easy to use and it works. It's not necessarily recommended. So yeah, these would be in the IO monad. Typically speaking, you'll kind of create like a what's called like a monad transformer stack for your particular application. So I might have like a web app transformer that allows me to ask for the current user from the database, send messages to syslog, ask for the current time, and I kind of say like, okay, this stack is allowed to do these effects. One of them would be logging. Anyone else? Yeah.
You mentioned you had 45,000, give or take, lines of code, and that you found maintainability not, too difficult in terms of refactoring. Do you find that it seems like that's a low count? Is that because of Haskell? And do you think that the strong typing really helped? I guess some of us are very familiar with stringly typed, where
Yeah.
you make a change one place, it propagates everywhere, but everything compiles cleanly, right away. Some people like that. Do you think that's perhaps a bad trade-off there, or getting all the errors up front, has that discouraged people, or just it is better to know?
Yeah, so there's a few good questions in there. So the first one is kind of comparing it to stringly typed programming, which is basically where you're still kind of using types, but you're pretending everything's a string. So email address is a string, name is a string. And that sort of gives you some advantage that you're not mixing up strings and integers. But you're kind of forcing to deal with the mistakes that we all make at runtime. There certainly is a trade-off to getting all of or most of your errors at compile time. And to an extent, I think it's a little bit of a personal preference. I think anyone that tells you that like dynamic typing or static typing is better is probably wrong. That's it's kind of a personal preference, or at least that's my belief. It can be extremely frustrating to spend a week doing a refactor and not even run the program. And it takes like a different mindset to be okay with every day just fixing compiler errors and not actually running the program. When I started facing that, I started, sort of just questioning the alternative. Is it really that productive to be running my program and like debugging, okay, I'm getting an exception here, but it's because way over here in the chain, I passed a user ID instead of an email address. That sort of like feels maybe artificially productive because I'm like debugging this interesting problem. But I started to question whether that was actually a productive use of my time. Like, sure, I'm running the tests and running my program, but like, does that mean that I'm getting more work done? I don't know.
So Reid, what do you attribute to the team's ability to move faster as you've amassed more code? Is there something inherent in Haskell? Is that some other modularization scheme you've put in place?
Yeah, so I think it could be done in any language. Haskell, for us, I think makes it a lot easier. We have a tremendous amount of like shared library code that represents our domain. So we have a monorepo. Our 6 services all import our sort of shared code base, do some HTTP and JSON database sort of manipulation around it. But when we sort of change the shared code that represents our domain, so like the user to organization change, that's a real refactor that we made. We made that in kind of our core shared code that's shared between our services. And then all 6 of our services failed to compile. And we had to go fix them. And so in like a single atomic commit, we implemented this feature, and now all of our services are up to date. So yeah, I guess the short answer there is we just get a tremendous amount of code reuse. Like imagine in Rails you have some function that's like get user, and you're starting to write a Sinatra app. You kind of have to ask yourself, like, does get user do some Rails magic? Is it just reading a cookie from rack or something? In Haskell, I know exactly from the type, can I use this in some other context? There's no way that it's using some other state. It does exactly what it says. So if it's a pure function, I can for sure reuse it in any other part of my library. There's no sort of like hidden state dependency there.
You went briefly over a quick check, and I think there's going to be another talk actually about property-based testing as well.
Oh,
I think
cool.
There was one yesterday. How helpful do you think that property-based testing has been in terms of weeding out logic errors and helping you move quickly versus, say, traditional unit testing? Because I know unit testing is still the soup du jour at a lot of places, and it only tests what you write the tests for, and keeping the tests up to date is often work.
Yeah, so first I would say property-based testing is not at all specific to Haskell. So if you leave this talk and you're like, oh, property-based testing is cool, but I don't want to use Haskell, you can totally do that. There's property-based testing libraries for a lot of different languages. Some of them are actually better than Haskell's quick check. I'm a total property-based testing fan. I think it's tremendously valuable. In our code base, we actually write a lot of like integration tests that are property-based tests. And I think it gives us the ability to be sure that we don't have, or at least to be more confident that we don't have the type of edge cases that just take like man weeks to figure out. Some of you have probably used Pivotal Tracker before. So they had a UI bug that had been around for 4 years that they would get occasional reports from their users about. So in Pivotal Tracker, you have like some stories. It's a web application. You can kind of drag them around. And there was some like weird scenario where they would drag some things around, and I believe like a story would just disappear. And it was one of those like Franken bugs that they'd get user reports, and the user's like, I don't know, I just moved some stuff around. Obviously, it wasn't specific enough to sort of figure out what the exact issue was. And in a completely unrelated exercise, they started using property-based testing to test their front-end code and came up with some properties like, if I rearrange the stories, they should all still be there. And the very first time they ran the test, it found this bug that had been like a Franken, sort of user experience bug for like 4 years. Not every time you run it are you gonna sort of get that kind of return on your investment, but I found that you find just really interesting bugs, and every time I like press enter before the first time that I write a property-based test, I'm just like kind of curious to see like what strange edge case is gonna find. It looks like we might have time for one more. All right, well, thanks for listening.